All right, good morning. Thank you all for being here, and thanks for having me in this session. Today I want to talk a little bit about using an Earth system model to kind of explore the variability in oxygen isotopes over the Quaternary with an application to monsoon regions, particularly Indian monsoon in this case. And I just want to acknowledge my collaborators from the National Center for Atmospheric Research, GIS, University of Wisconsin, and Oregon State University. So a little background about the model I'm using today. It's the Community Earth System Model, version 1.2. It's maintained by the National Center for Atmospheric Research. And this version of the model has water isotope tracking of deuterium and oxygen in all model components, including the atmosphere, the ocean, the land, and the sea ice. And this was a large collaborative effort involving NCAR, University of Colorado, Oregon State, and University of Wisconsin-Madison. And if you're interested in more details on the model components, be sure to check out some recent publications in James and some work soon to be out in the Journal of PNAS and GRL. Cool. All right, so the simulations I'll be talking about today are tin, and these tin simulations have different in-member forcings that are roughly representative of the late of the Quaternary, mainly the late Pleistocene. So I have a pre-industrial control simulation. I have a simulation with low obliquity, with the other variables held at their pre-industrial values. I have a high obliquity case. I have 4 combinations of eccentricity and precession. I have a 0 eccentricity case. I have a half CO2 case compared to pre-industrial, so this is 142 parts per million. And I have an LGM land ice and sea level case. So these roughly encompass kind of the in-member forcings of the past 800,000 years or so. And these all have water isotope tracking in them. So the motivation behind this work was really to better understand the large-scale water isotopic responses to these kind of in-member forcings. But even more than that, hopefully we're trying to be able to see if we can actually reconstruct individual proxy records using a combination of these in-member forcings. And this work was motivated by some other work that suggested that these linear combination of different in-member forcings actually do a fairly good job at representing the complete signal. So, for instance, we have these different equations and these different in-member forcings, and for example, you could take the low obliquity case minus the high obliquity case to get the amplitude of the obliquity signal, and then you can scale that by known variations of obliquity through time. And we can do the same for eccentricity and precession, the same for greenhouse gases, and for sea level changes. And this has been shown to work fairly well for temperature and precipitation at getting the complete signal, especially in the low and mid latitudes, so it should work fairly well for water isotopes as well. So today I'll just be giving an example of how we can utilize these experiments to understand proxy records, and in this case I'll be using the Bit2 cave site as an example. This is a cave in northern India that has about 240,000 years of signal with very good dating and only a few hiatuses. So here is the smoothed record for the past 200,000 years at the Bit2 cave site. The mean has been removed and it's been smooth. And then we can add on top of this our linear reconstruction. So plotted on top of this is our reconstruction from our model signals. And this is based on the delta 18O of the soil water and a small correction for annual mean temperature change at the cave site. And so overall, you can see that the model's doing a fairly good job getting the amplitude that the cave site's suggesting, as well as some of the signals in precession and glacial interglacial cycles. And on the right over here, you have just the scatter plot relationship, between the change in delta 18O with the change in model delta 18O. And if you want to look at this in a bit more detail, hopefully you can see is that these are the various contributions from the different signals that go into this complete reconstruction. So in blue you have the change due to changes in land ice contribution, the change in greenhouse gases in orange, obliquity in green, and the very large precession signal in purple. Then we can look at this in a different way. We can look at how the changes in delta 18O of the model at the cave site relate to changes in precipitation and temperature. So I have changes in delta 18O on the y-axis against precipitation in this first plot here. And you can see there's actually a fairly good correlation. So the red dots are the complete reconstruction, and then there's the various signals in there. And And there's a pretty strong relationship because the precession signal is really dominating the change in precipitation. And so even though obliquity might not have the same slope as precession, it gets dominated by the precession signal. If we do the same thing for temperature, as shown on the right here, the relationship's not nearly as strong. So different signals have very large annual mean temperature changes, and they don't really correspond with the changes in the cave site. And that's some things that have been kind of inferred earlier from previous studies. But we can really go into more detail with these model experiments and try and understand exactly why we're getting this large variability. And so we can do that by looking in more detail at the precession signal. So here's the change in precession through time. And from here on out, I'm kind of begin doing this by looking at kind of the in-member precession experiments. So I have Northern Hemisphere summer aphelion, which is 90 degrees of precession, and Northern Hemisphere summer purhelion, which is 270 degrees of precession. And during Northern Hemisphere summer aphelion, you have a very enriched signal at the cave site, and converse is true for Northern Hemisphere summer purhelion. So we know that there's a lot of factors that go into determining the isotopic signal at a certain site. You have changes in precipitation intensity. This is the amount effect. You have changes in where your water vapor is coming from, potentially. Changes in the water vapor composition, not in just where it's sourcing from, but also changes in how it's raining out before it gets to the cave site. You also have seasonality of precipitation, which can affect things, local evaporation signals, and a small temperature signal as well. And hopefully I'll touch on most of those in the remaining of the talk. So one of the biggest contributors to the signal, as has kind of been alluded to earlier, is the precipitation change signal. So this is considered the Mount effect. And here I have summertime change in precipitation between 90 degrees precession minus 270 degrees precession. And what you can hopefully see is that at the cave site, there's a significant decrease in precipitation during Northern Hemisphere summer aphelion. And so that's really just, you're getting much less intense precipitation during this time, and as such, you're getting less rainout. You're getting more of an enrichment signal due to that contribution. And we can look at this as a monthly signal as well, and so here plotted in red is the change in delta 18O at the site through time, and in blue is change in precipitation. And what you can see is that when you get a significant decrease in precipitation during 90 degrees precession relative to 270 degrees, you get a significant uptick in your enrichment signal. So there's definitely a large amount effect playing a role here. However, I don't think that's the only contribution going on. We can look at this in more detail by tagging particular water regions. So what we can do is we can select a certain area in the climate model and try and look at where that precipitation is sourcing from originally. And so we did this with a lot of regions around Asia, and we found that there was 3 main regions that are really contributing the majority of the moisture to the cave site. Those include the Indian land surface, and so there's recycling there. We also have a significant signal coming in from the Arabian Sea and the Southwest Indian Ocean. And these main signals don't really change between Northern Hemisphere aphelion summer and Northern Hemisphere purhelion summer. So here's a plot of summertime change and near surface water vapor, delta 18O, between 90 and 270 degrees precession. And the boxes here are the 3 main moisture sources for the cave site. And so the red one is just for over land, and the blue ones are just for over the ocean. And a few things to point out here is, one, we're getting a very significantly enriched signal in a lot of these moisture sources right by where you're sourcing the water from. And so that's suggesting that the water vapor, before it even makes it to the cave, is already enriched. And this is largely related to changes in the sources from the ocean. So in this case, we're getting a significant, this is a plot of delta 18O of the upper levels of the ocean, and it's suggesting that we're getting a very enriched signal during Northern Hemisphere aphelion summer. And so you're just sourcing much more enriched values to begin with. That's largely due to changes in runoff and evaporation minus precipitation, as well as some changes in circulation. And so here I've just plotted salinity as an example of how we're getting more salty water there, and therefore an enriched signal. We also have some changes in where the moisture is sourcing from. So in Northern Hemisphere aphelion summer, we're getting relatively more. So overall, we're getting less precipitation, but the percent of precipitation is coming more from the Arabian Sea, the Bay of Bengal, and the Indian mainland, and we're getting less from Northern Africa, the Indian Ocean, the Middle East, and Central Europe. And so we can look at that visually here again, as this is summertime delta 18O of the vapor near the surface, and on the left is where we're getting less precipitation sourcing from, and on the right is where we're getting more. And there's a few things to point out here. First, where we're getting less precipitation are further away sources. So you would expect those to be more depleted just because they're getting more rain out possibly before they get to the cave site. And then these ones are closer where we're getting more precipitation. So they're closer to the site, less likely to have rain out before they get there. But on top of that, where we're getting less precipitation, you have more depleted signals, but where we're getting more precipitation from, it's very enriched already. And so there's contribution going on from there as well. So that helps to explain really why we're getting differences in our delta 18O precipitation, but not necessarily our complete signal. So as I mentioned earlier, and this is our complete signal over here on the right, we're getting a very large amplitude signal, but this is coming from the delta 18O of the soil moisture. So on the left here, I have the precipitation weighted delta 18O of the precipitation, and what you can see is that the amplitude of our reconstruction in red is significantly smaller than the one using the delta 18O of the soil moisture. And so this difference in delta 18O between the precipitation and soil moisture can be seen visually here. And so you have a significant enrichment here in precipitation between 90 and 270 degrees per session, but it's not nearly as large as you get in the difference in the soil moisture. And this largely has to do with an evaporation signal. So you're getting a much more arid climate during northern hemisphere summer aphelion, which is enriching your signal. And we can look at the changes in evaporation minus precipitation. This is just the annual average here. And you can see that in a lot of these regions where we're getting a significant enrichment signal of the soil water delta 18O, we're also getting a lot more evaporation during this time. Finally, there's a small temperature contribution to this as well. And so I'm using the standard, which is about 0.24 times the annual mean temperature to correct for the cave site. And the reconstruction, the total one, is in red here for the temperature contribution. And so you can see it's relatively small magnitude, but it does help to improve our agreement between the model and the proxy. So I think it's a valuable contribution. And if you look at this, you're just getting about a 2 to 3 degree warming in a northern hemisphere summer aphelion minus perihelion. And this is largely due to a much warmer winter climate state, not really the summer. So hopefully I've shown that these single forcing simulations can help us to understand some of the more detailed nuanced changes in what's causing them in these speleothem records, and this can be applied to many different records. This is a global data set, so we can look at this in, for instance, Antarctica as well as deep water in the North Atlantic. And for this particular cave, we found that the amount effect was definitely an important player, but there's also significant changes due to moisture sources, aridity, and temperature. Moving forward, I'd like to use this with model-specific proxies to get a better handle on what's actually happening after it precipitates and how it runs into the cave system. And then also tagging the actual water isotopes at the source regions to get a better understanding of how the delta 18O is changing from the source to the destination. And so that's all I have. If you're interested in these experiments, please let me know. I'm happy to talk with you about how they can be used potentially for your site as well. So, thank you.
The question was how your land surface was treated in your modeling regime.
Yeah, so it conserves water like the standard CLM4, this CLM4, if you're familiar with that. And so you have 10 soil levels, I believe, and water is able to circulate through it and run off anything that comes from the atmosphere into it, and then evaporation from the surface, as well as evapotranspiration from the vegetation as well.
So we changed completely going to data from the triangle fraction of the sediment, and these are the results obtained by Chen, who he passed his PhD last December, and he's in Shanghai, so it's my duty to present his results now. So the South China Sea is a peculiar location. It's in the Indo-Pacific whirlpool, as you can see here, and it is also in the East Asian monsoon area. So during the summer precipitation, very large amount of sediment discharge occur in the South China Sea, and they are distributed that way around the South China Sea. Here it is expressed in millions of tons per year. And there are three of the world-class rivers: the Pearl River, the Red River, the Mekong, and many mountain rivers on the other side of the South China Sea delivering this sediment. That we are expected to be very variable in composition because the climate is different. Although we are in the monsoon area, the seasonality and precipitation rate is quite different from 25 degrees north to the equator, and the geology is different in the different catchments as well as the tectonic. When the sediment arrives at sea, it's taken by the upper water masses that are seasonally changing related to the monsoon winds, and we also have the currents, the upper current coming from the Pacific and entering in the South China Sea, as well as the deep current here redistributing the sediment along the western coast of the South China Sea. During glacial stage, the situation was different due to the very large shelf here, which was emerged during low sea level, and which brought the mouth of the rivers closer to the deep basin, and which made also the South China Sea a semi-enclosed area with the only connection with the Pacific through the Luzon Strait. So to study the past variation of the environment in that area, we took a course in 2012 from the Marion Dufresne. Many courses have been studied in this area, but they are short courses, multi-proxy analysis, but on a short period, or a very long period with ODP site, but at lower resolution, and not always multi-proxy on the detrital part of the sediment. Here we deal with this 51 meters long core at about 2100 meter water depth. So this core is fed by three different areas as far as the detrital fraction is concerned, and these have been characterized in the rivers by the clay assemblage that you see here. The river is kaolinite. Kaolinite takes a very long time to form, and illite and chlorite are the same as in Taiwan, except for the crystallinity index of illite, which makes the two very different. And smectite is the majority in Luzon, and it's produced by very quick weathering due to the precipitation. In the magnetic fraction that we also analyzed in the same river samples, we have pyrrhotite coming, characterizing Taiwan, and magnetite is more common magnetic mineral. But you see that it doesn't come from alteration, so the clays and magnetic fractions are very complementary in the information they give. We have a little bit of hematite in the Pearl River, but I will go back to that later on. It's only on tributaries. So first we start with the age model that we took advantage of the age model of ODP site 1146, which is close by, with the planktic isotopes which has been correlated to speleothem, and benthic isotopes that we, for which we prolongated the age model with respect to this one by orbital tuning. This core has carbonate calcium record, which is very similar to ours. Ours is more detailed, but it looks pretty much the same. And so we correlated the two in order to transfer this age model to our core. And we have a sedimentation rate, which is on the average 13 centimeters per kilo years, and it covers the last 400,000 years. So we examine all these proxies, and we'll start with the clay mineralogy. Here it is. It's dominated by smectite, followed by illite. You have the percentage, which is the average here, illite, chlorite, and a minority of kaolinite. And when you plot the ternary diagram with the river samples that you have here, you see that our core is a mixture of everything. So illite can come from the Pearl River, from Taiwan, but as I said before, with the crystallinity index, which are very different from the two areas, we can distinguish, and our record is here, so it's illite is coming from Taiwan. So the three sources are contributed to the clay mineralogy of this core. So I forgot to say that this is published in the scientific report and in 2017. So you see that besides the average value that we have here, we have time variation of all these clays within the clay assemblage. Kaolinite is having its own life, I would say, different from the others, but it's quite clear that illite and chlorite are similar, and we can better judge by superimposing the two. And now we see that they are also anti-correlated to smectite, and we see that better if we reverse the scale of this one and we superimpose smectite, and you see how they fit together. So the kaolinite, which represents the Pearl River signal, has a clear eccentricity periodicity. And now if we calculate the smectite over E-light plus chlorite ratio that is here, and which illustrate the precipitation, because smectite is a product of very fast weathering and indicating the precipitation rate with respect to the other proxies, we see that we have a very weak eccentricity cycle, and it's dominated by precession cycling. So we see that better with the spectrum analysis of the two records, where you see that in the gray curve, the 23 kiloyears dominates largely, and in the kaolinite, it's the 100 kiloyears. I'll come back to that later. The magnetic properties of the cores, you see that these are the bulk parameters with a loss of signal here in the fine particles, and this is due to partial dissolution, as shown also by the magnetic grain size. And this is partial dissolution, but if we enhance this part, we see that the variation are the same as the red curve. So we can still believe in that part. And we also have difference in the magnetic mineralogy here, because these three parameters are sensitive to these two, grain size and magnetic mineralogy. I will keep these two signals, forgetting about the top part, which is dominated by magnetite, and I will enhance the bottom part of this one, of course. So these are the two records from 80 kiloyears to 400 kiloyears. We add here a proxy for grain size, which is the sortable silt, which is between 10 and 63 micrometers. And I'll show again with the benthic isotope and the eccentricity cycling and the kaolinite. And you see that each record is showing a clear cyclicity here. And during glacial period, which are the blue one here, we have more kaolinite, coarser grains, magnetic and silt grains, and more magnetite, pyrrhotite with respect to hematite. And this is clearly something which is due to the low sea level and not to bottom current, at least in our case. The more proximal to the mouth makes the kaolinite increasing because it's deposited close to the mouths of the rivers, and magnetite, pyrrhotite come from the erosion of the shelf where they have been deposited during high sea level. So the low sea level is playing a dominant role in this. Now, if we forget about these results and we go back to these ones, and we add another one for the magnetic mineralogy, which is the pure content in hematite, while here it's relative content. We also add the precipitation proxy that I have shown before, so the East Asian monsoon proxy. We see that they are all dominated, not dominated, but the 23 kiloyear periodicity is present in all of them. And it's in phase with the North Hemisphere insolation. So during weak precipitation, we have finer grains and more hematite. So where do these hematite and finer grains originate from? That is the question at the precession scale. We thought about the Pearl River. This is the study we made of the river samples. Hematite is toward the yellow and red colors, and you see that they are only identified in these tributaries, and so it's very unlikely that these were winning during a weak precession, minimum of precession with respect to the mainstream of the Pearl River. There is no reason. So the other source we could think about is the aeolian input. How can it work? It can work either with the desert we have here, but the westerlies are described as being much farther north than our area. However, in these cores, which are at about the same latitude, the authors also recognize some dust. If it's linked to the winter monsoon, enhanced winter monsoon, we should have this dust, but also coarse grain, because the transport vector is more efficient. There's another possibility which has been invoked by these authors, Ray and Shu et al., which is that the fine particles are going to the troposphere and they get down with the rains. And when the summer monsoon is weaker, this is pushed toward the south, and so the dust rain is also toward the south. So this would be due, in that case, to the weakened East Asian monsoon. And Nakashima et al. In 2011 published that figure, which show a shift, north-south shift of the westerlies jets. And he studied another period, another time scale, but we can make maybe the parallel between this scheme and the weak East Asian summer monsoon, whether you see that the jets are southward, so they would bring more dust, maybe not from this desert, but from other sources in this area. So in conclusion, and this is in press in EPSL now, it should be in press very soon. We should receive the proofs in the next days. We took advantage of the varying heterogeneous assemblage in this core. On the glacial interglacial scale, it is the sea level which wins in being at the origin of the observed variation. The increased mectite over elite plus chloride ratio in the clay assemblage during the high north hemisphere insolation is illustrating an increased fast weathering due to high precipitation rates. So it's proposed as a tracer for East Asian summer monsoon in this area. And on the other side, the increased hematite inputs together with fine silt grains may be interpreted as weak East Asian summer monsoon. I put a question mark here because we need more we need confirmation for other cores. We were very fortunate here, I would say, as paleomagnetists, we don't like dissolution, but we were fortunate to have the magnetite dissolved, because to see hematite, it's a challenge. Magnetite is much more strongly magnetized than hematite. So to see it, we need to take a little bit to remove some magnetites, and this was made by dissolution, and I think this is how we could see the hematite signal on that scale, precision scale. Thank you.
Do you plan to characterize your fine silt grains, like with map observation, what it is, what type of mineral it is, and things like that?
Yeah, this was planned and could not be done in the time of Chuan's thesis, but we are carrying on our investigations on different methods, using different methods to try to in fact characterize. I didn't show it because I couldn't show everything, but we have the major elements and trace elements using XRF scan, and it goes also very well with the SE silicium and quartz signal. So it's a good argument as well, because desert dust is not only hematite but also quartz. But we need to have a look to how these quartz look like, because they are,
Today I'm talking on plank foraminifera assemblage changes in the north-south transect of Andaman Sea for understanding the paleo-monsoon conditions. So as we know, in India, monsoon is an important parameter. The picture itself depict what is the importance of monsoon. Some season we are getting intense precipitation. There are sometimes drought conditions. So it itself shows the importance of monsoon. So in order to understanding how the monsoon is varied in the last deglacial times, especially for the last 30,000 years, have studied some cores taken from the Andaman Sea. It's in the north-south transect. The northernmost core, you can see SK168. And centralmost core and southern core, and this almost all these cores are nearly 4 meter length. And Andaman Sea is an important, it's a marginal AC. It's when comparing with the Bay of Bengal, you can see some changes. For example, temperature in Andaman Sea, deeper water is more warmer than Bay of Bengal, and similarly salinity also you can see there is a change. Like dissolved oxygen, there is a change, mainly because there is you can see some sill which prevent the good circulation between Bay of Bengal and Andaman Sea. So another important oceanographic changes we can see in Andaman Sea is there is a salinity changes. Because of huge freshwater runoff and direct precipitation, we can see a north-south salinity gradient. So even in the northern part of the Andaman Sea and Bay of Bengal, salinity is very low, and southern it's up to 35. There is a salinity gradient 7 PSU. So as a result of this, there is changes in foraminifera assemblage, especially plankton foraminifera. So in Andaman Sea, we cannot see much studies. Almost all the monsoon reconstruction we can see from Arabian Sea. So there they mainly use the wind patterns. But here Andaman Sea, because of these salinity changes, we can use this for understanding the past monsoon variation. So this is a methodology. Have sample processing, C14 dating, then basically plankton foraminifera assemblage analysis, reports, and some geochemistry and oxygen and carbon isotope analysis. So we have rich assemblages for plankton foraminifera. Nearly 35 species are identified from the Andaman Sea. Among that, these are the most dominant species. Rhubarb, it's nearly 21% of total assemblage, followed by glutinata, dutta tree, bulloides, and obliculata. So this is the most abundant 5 species in Andaman Sea. So if you see the present seasonal variation, so first one is bulloid, second one is dutta tree. So during peak summer monsoon, we can see a huge abundance of bulloides as well as dutta tree flax. So bulloides is considered as, in Arabian Sea, is considered as upwelling species, as a productivity species. In Andaman Sea, so there is no trap record from Andaman Sea, but we have trap record from Bay of Bengal. In Bay of Bengal, the trap shows that bulloides shows a prominent peak during summer monsoon. Similarly, dutta tree, it's identified as a low salinity species. Its abundance very high during and salinity is low. So these are the 2 species I have used for interpreting paleo monsoon. So this is the record. The first part you can see I compared the productivity proxies record, salinity proxies record, and stratification. So the interesting thing is that during early Holocene, when the summer monsoon is strong, we can see productivity, very low abundance of productivity species like bulloides, falconensis, glutinota. So similarly, if you see the salinity proxy, the early Holocene and mid Holocene, the summer monsoon is very strong. As a result, there is a collapse in productivity. That is mainly due to the stratification event. At present also in Bay of Bengal, if summer monsoon is strong, there is a strong stratification due to freshwater runoff. So as a result, like in the Bay of Arabian Sea, we cannot use these bulloides as a appalling species in Andaman Sea for monsoon, but we have to use some carefully. But in bowling alaroid and during other deglacial times, we can see a increase in bulloides, which is parallel with the increase in summer monsoon. And you can also see in the dutta tree, there is increase in strength in the deglacial structure, and it's highest during the early Holocene, again followed by highest in the mid Holocene. So this is the 2 period when summer monsoon were strong. So it is parallel with stratification event. And if you see the stratification proxies like oxygen isotope, you can also see the early Holocene and mid Holocene stratification event. So this is the important species abundance, mainly productive species abundance in the northern core of Andaman Sea. So here bulloides, glutinata, bulloides and rhubarb, and some of the geochemical proxies. So these 2 periods when summer monsoon were strong, like in the early Holocene and mid Holocene, productivity species are very low. So this is the second core. It's in the central Andaman Sea. Here also early Holocene and mid Holocene, the productive species are very low when summer monsoon were strong. So this is the third core. Here also the same. The early Holocene increased summer monsoon is not seen in the productivity species. That is mainly because of stratification. So this is the comparison of monsoon record from the Indian Ocean and other available records. So here, so because of that, we used mainly dutta tree for interpreting paleo monsoon, because it's a good indicator of salinity changes. So we can see the intensification of summer monsoon started somewhere in the bowling alaroid. We can see a low abundance of dutta tree species mainly during younger Dryas, followed by there is increase from the early Holocene up to mid Holocene. So the major conclusions drawn from this study is that there is a, due to the location of northern core shows highest variability, because the freshwater, lot of freshwater is reaching the northern part of Andaman Sea. And intensification of the Indian summer monsoon started in the early stages of bowling alaroid, followed by slight weakening during the younger Dryas, and regained the strength during early Holocene. The enhanced summer monsoon during early Holocene resulted in huge freshwater runoff, resulted in the stratification and productivity collapse. Two stratification events were seen during early Holocene and mid Holocene. A progressive gradual decline in the tundra foraminifer abundance from mid Holocene to present suggests gradual weakening of ISM. Thank you.
I'm here to present my work on about the influence of carbon dioxide, the Antarctic ice sheet, and Asian topography on the Asian monsoon and regional moisture variability. Actually, all of those three parameters are proposed to be the driving mechanisms that are driving climate change in Asia during the Cenozoic. So our approach will be a modeling approach about the sensitivity of the climate to each and every one of those parameters individually. What is interesting about Asia is that it consists of really diverse climates ranging from Arctic to subarctic to tropical, while when we move to the south and the east, the environmental conditions are dominated by the monsoons. And Central Asia, which is quite an interesting place, to the north of the Tibetan Plateau, is actually characterized by arid conditions. We carried out simulations using the HAD-CM3L model, which is a model of the UK Met Office, a coupled ocean and atmosphere general circulation model that actually consists of dynamically coupled atmosphere, ocean and sea ice models, with a horizontal resolution of 2.5 degrees in latitude by 3.75 degrees in longitude. And it has 19 and 20 levels, vertical levels for the atmosphere and the ocean respectively. The model has been evaluated, is actually widely used by paleoclimate modelers, and it has been evaluated for the representation of the monsoon. And we can see that the precipitation and the SST as well as the winds are very well represented, so we can actually be very confident about those results. What we did is we performed 7 experiments, the first one being the control experiment for the pre-industrial control experiment, and then for each and every one of the components we're trying to study, we did 2 different simulations. We carried 2 different simulations. For the carbon dioxide, we had 2 simulations, the PI1 and PI2. In PI1, we doubled the CO2, and in PI2, we took 4 times the CO2 of the pre-industrial era. And then we moved to the pre-industrial with no ice sheet coverage in Greenland, and PI4, which was the pre-industrial with no ice sheets. And then we moved to something more radical as a change in PI5 and PI6, where in the first case, we actually flattened the whole Himalayan area and took it to sea level. And then the last experiment was performed with the Oligocene-like Himalaya, which is roughly 2.5 times lower than the modern elevation. As you can see in the pre-industrial experiment, the precipitation is simulated and follows the monsoonal pattern. This is the boreal summer average of precipitation, where it's the shaded part here and the observed precipitation. And also, we did that with the winds, and you can see that the winds are, the reversal of the winds, which are marking the onset of the monsoon, are really, really well represented, and not only in the directionality, but also in the strength, as you can see, if you compare it with the observed winds. Moving on to the sensitivity experiments, you can see here what happens to the precipitation during summer when we double the CO2. You can see an increased precipitation around the equator over here, and in the Indochina Peninsula, and the increase is up to 20% the pre-industrial, which actually is increasing more when we move into the conditions with 4 times the CO2, which is PI2 here. You can see that the maximum precipitation, which is here and here, is 40% more than the pre-industrial, But what is really interesting about that is the drier conditions that are now here around the equator. And that can actually be explained since we're 4 times more the CO2 from the pre-industrial, we move into warmer conditions, so that actually indicates a shift of the intertropical convergence zone towards the north. When we remove the Greenland ice sheet, you can see virtually no change here. It's less than 3%, so it's actually negligible, but that is not the case when we remove all the ice sheets. That means Greenland and Antarctic ice sheets both. You can see that in that case, the rainfall increases by 25% in those areas here, while we have a high magnitude decrease around the South China Sea. Moving to the more interesting results, when we have the flattened Himalaya simulation, you can see that the whole Tibetan Plateau area switches into drier conditions, and that actually extends over here into the Bay of Bengal, also around the equator. The increased precipitation, which is located here and here, the maximum increased precipitation, which is right here, reaches up to 30%. And finally, moving to the Oligocene-like Himalaya, you can see that the drier conditions are also persistent here around the Tibetan Plateau, but this time what changes is that we receive more precipitation into the Bay of Bengal and over India, over South India, and that actually is about 38% more than the pre-industrial. Wanted to focus more on what is happening in the areas that are affected by the South Asian monsoon than an East Asian monsoon. We calculated the weighted precipitation average for those areas, as well as the area which is the Asian low pressure system between the two pressure highs over Asia. And you can see from this bar chart here that the South Asian monsoon is the region that is affected the least in comparison with the East Asian monsoon and the Asian low region. The rainfall over the East Asian monsoon and Asian low region presents a decrease of more than 35 and 100% respectively for the simulations where we actually flatten the Himalaya and we have the Oligocene-like Himalaya. And finally, you can see that the precipitation changes for for the experiment where we remove the Greenland ice sheet, also negligible here. But actually, that started to raise some question as to what's happening to the monsoon precipitation domain, and if the precipitation changes we see are actually associated with the monsoonal precipitation. So we used these two criteria to actually define what is a monsoon precipitation domain, and that's actually the areas where both of those criteria are met, where actually boreal summer and boreal winter precipitation difference is greater than 2.5 millimeters per day, and when summer precipitation exceeds the 55% of the annual. As you can see here, in the pre-industrial control pattern actually is really similar to all the experiments, to the doubling of the CO2, 4 times the CO2, no Greenland ice sheet coverage and no ice sheet coverage at all. But that actually changes radically when we move into the simulations with the Himalaya. You can see that when we actually flatten the Himalaya, the monsoon precipitation domain actually shrinks, and it's focused mainly here over the Bay of Bengal and the South China Sea. And when we actually go to the Oligocene-like Himalaya setup, you can see that actually is focused around the Bay of Bengal and the eastern part of India. Moving on to the winds, you will see in the first column, you will see the pre-industrial control, so you have something to correlate with the results. Then in the next column, you will see each and every experiment on its own, and then there's the difference, which is the sensitivity. The first one is when we're doubling the CO2, you can see that there is not much change going around. There is only a slight increase of the westerlies over here around the equatorial Indonesia. And that seems to be the case for when we actually go into the 4 times CO2 experiment, but there's a slightly more strengthened winds here, the westerlies, and we also see here a small increase in the easterlies around the equator. As it was with precipitation, when we remove the Greenland ice sheet, there is virtually no change, so it seems like it doesn't affect the whole system at all. But that is not the case for when we remove the whole ice sheet coverage, that's Antarctica. You can see that when we remove that, the westerlies over here off of the coast of Africa are increasing, and that is the case also for the equatorial Indonesia over here, where both westerlies and easterlies are increasing. What is really, really interesting, once again, are the two last experiments, the Oligocene-like Himalaya and the flattened Himalaya, where you can see that we have a great change in the winds regime over there. What you don't see in those diagrams is that when we remove the Himalayas or even flatten them, we don't see any change at all at the southern hemisphere, so all the change is actually happening to the northern hemisphere, especially over the Tibetan Plateau. Now you can see that when we remove the Himalaya, the Tibetan Plateau, we flatten the whole area, we can see now the westerlies not being blocked by the topographic barrier that the Himalaya is, but actually we have the westerlies crossing in inland Asia, which indicate that that's maybe a moisture source that when the Himalayas are there, they are blocking it. That same thing goes with when we have the Oligocene-like Himalaya setup. Again, the westerlies are crossing inland to the Asia, but not with the strength that it seems to be the case when we have the flattened Himalaya. To sum up, even though the precipitation change do not seem to affect Central Asia, this is not the case for the westerlies, which are considered as the main moisture source for inland Asia. With the Himalaya flattened or significantly decreased to simulate the Oligocene configuration, the westerlies are now stronger and crossing the inland of Asia, since the Himalayan origin is no longer acting as a topographic barrier. In the two experiments with the Oligocene-like Himalaya and the flat Himalaya, we can see that the regions with the increased westerlies strength coincide with the areas showing an increased precipitation, except for the region over the Tibetan Plateau, where the origin is not there anymore. When the South Asian monsoon area shows a small fluctuation in terms of precipitation, but the Bay of Bengal and the China Peninsula receive more rainfall from the two Himalayan configurations, and as you saw on the slide of the monsoon precipitation domain. Finally, the precipitation in the East Asian monsoon area presents a significant decrease with Himalayan boundary condition changes, even though the wind regime, as I showed you, remains relatively constant. Thank you.
Question about this. I think you attribute to the increased precipitation in the 4x CO2 experiment to the northward shift of intertropical convergence zone, right?
You mean about that, right? Yes.
Yes. I'm just wondering, what about the role of the increased relative humidity in the atmosphere at 4x CO2? Because when you increase the CO2 concentration, of course, the relative humidity in the atmosphere also increase. So
I haven't had a chance to look at those parameters yet, but we will look into those too.
Yeah. Okay. Thank you. And can I ask one more question? So
Please.
when you change the ice sheet over Antarctica and also the ice sheet over Greenland, so what about the interhemispheric temperature gradient changes? As we know, the present day that in the pre-industry, I think the northern hemisphere is about 1 degree warmer than the northern hemisphere. That's why the ITCZ is located in the northern hemisphere.
Mm-hmm.
So after you remove the ice sheet over Antarctica and also the Greenland, what's the location of the ITCZ and what's the interhemispheric temperature gradient? So
I don't know about the temperature gradient, but the intertropical convergence zone is actually also moving towards the north in that too.
Okay.
But it's way more evident than that 4x CO2, that's why I mentioned that there.
Do you examine the global monsoon domain?
The global no,
Yeah,
I'm focusing in
response, yeah.
Asia.
Okay, good morning, everyone. My name is Jongmin Lee, and I am a PhD student at Pusan National University in Korea. First of all, it is my great honor to have an opportunity to give my presentation in FAGE Open Science meeting. Now I'm currently studying the interaction between monsoon and climate change, using the IRP Expedition 353 course. Today, I'd like to talk about my result on long-term variation of clay mineral compositions at site U1447 in the Andaman Sea. Okay, let me start my presentation. We already know that the formation and transformation clay minerals are determined primarily by the interaction between the geology and climate in the south region. Especially climatic conditions are of primary control clay mineral formation. And climatic changes potentially cause changes of clay mineral distribution in marine environment. So clay mineral abundance in marine sediment are useful indicator of paleoclimatic condition in the continental region. My study area is the Andaman Sea. This figure show, as you see, this figure, the Andaman Sea is characterized by the Indian monsoon. It shows that the seasonal wind direction and surface current. During the summer season, southwest winds and eastward surface current are dominant. In contrast, during the winter season, northeast winds and westward surface current are dominant. In addition, fresh water discharged by the Irrawaddy and the Shalin rivers depends on monsoon precipitation in this region. During the summer, large river water discharge transports a great amount of the sediment into the ocean. So we can expect that the Andaman Sea is ideal region to establish the relationship between sediment erosion and climate change in the continental region. For this study, we used the sediment core at site U4047 of IRP Expedition 353, which is drilled in the Andaman Sea. The site U4047 is located at a water depth of around 1,400 meters, and drilling penetration is around 740 meters. This site U4047 is affected by the Indian monsoon, and our study site in the Andaman Sea received large amount of the riverine sediment from the Myanmar through the Irrawaddy and Shalin rivers. So The main purpose of this study is to prove the major controlling factors for the long-term variation patterns of clay mineral compositions in the Andaman Sea during the last 10 million years. Now I will show you my research result. This slide is the age depth model for site U1447. It was established by using seafloor biostratigraphic and paleomagnetic data. It shows that the age of bottom of coral is around 10 million years. My study interval covers from 1 million to 10 million years, as you see red box. In this study, I measured 69 samples of clay minerals using XRD and 16 samples of strontium and neodymium isotope using TIMS. Okay, this slide showed a main result of isotope and clay minerals. First, this is down core variation of isotopic composition of neodymium and strontium. Most of the samples are measured for clay size fraction, but for data of these diamond symbols are used by bulk sediment. In general, both neodymium and strontium isotopic value are not much changes, and a little low strontium isotopic values isotope value. I'm sorry. Isotope values of these four samples are due to the grain size effect. Anyhow, based on these isotope results, we can know that the main source of region has not changed significantly since the later Miocene. Okay, let me explain the sediment source a little more. According to Damodara et al. 2016, there are four main source regions supplying sediment to the Andaman Sea, based on neodymium and strontium study. These are Indo-Burma-Akan region in here, and the Irrawaddy River, and the Shalin River, and Western Thailand. And then we added our neodymium strontium data to their binary mixing plot. As a result, we can figure out that the Irrawaddy River has played a main source of sediment in our study area. Now I will show you clay mineral data. Clay mineral consists mainly of smectite and illite, with a minor of kaolinite and chloride. Smectite contents are between 30 and 60%. Illite contents are from 20 to 40%. Kaolinite contents are from 10 to 20%, and chloride contents are from 5 to 50%. And we divided three stages based on the variation pattern of clay mineral compositions. From the bottom, in the first interval, all clay minerals show the mostly consistent variation, except for one interval in here. And in the second interval, smectite contents decreased gradually, whereas illite, caolite, and chlorite increased gradually. In the third interval, all clay mineral contents show the decreased and increased with large fluctuation compared to previous two interval. Okay, in this slide, I summarized our clay mineral data. As I mentioned, I divided three intervals based on the variation pattern of clay mineral compositions. If we compare the average of clay mineral among these intervals, smectite decreased from 55% to 39%, whereas illite increased from 25 to 33%. Chlorite also increased from 8% to 30%, but kaolinite is not much changed from 20% or 50%. So from the late Miocene to Pleistocene, smectite increased, and illite and chlorite smectite decreased, and illite and chlorite increased. Now I will explain the variation pattern of clay mineral during the last 10 million years. To simplify the fluctuation of clay mineral composition, we calculated the clay mineral ratio, smectite to the sum of illite and chlorite ratio in here. As you see, this ratio decreased from late Miocene to Pleistocene. The decrease of smectite and increase of illite and chlorite since the late Miocene may indicate the degree of weathering in the Irrawaddy River, because the main source was not changed, as I mentioned. We can expect that the increase of physical weathering in the source region result in the increased supply of illite and chlorite. In contrast, the increase of chemical weathering result in the increased supply of smectite. So this ratio may reflect the balance between physical and chemical weatherings. In the first period, this ratio was slightly increasing. It means that physical weathering was low at the Irrawaddy River during this time. In the second period, this ratio decreased gradually, which indicates the decrease of physical weathering. In the rest period, the physical weathering was higher compared to previous two intervals. And at the same time, such degrees of physical weathering may be related to the evolution of monsoon strengths. Okay, now I'd like to sum up the main points of my presentation. First, Neodymium stratum isotope compositions suggest that the Irrawaddy River has played the main source of sediment since the late Miocene. And second, increase of illite and chlorite and decrease of smectite during the last 10 million years may represent the enhanced physical weathering and depressed chemical weathering. And last, long-term variation of smectite, some of illite and chlorite ratios may be related to the evolution of monsoon strengths. Okay, thank you for listening.
If you want to know the weathering index, why not use some directly for example, the illite chemistry index by the XRD, or the illite crispness. And for the illite, because it's very easy to cover by the wind, it's wind-driven clay minerals. So you must explain the source and the transportation of the monsoon or by the river. Not just compare the clay mineral and show the monsoon gets weak or gets strong, I think. I mean, why not use more clay mineral proxies? Not only the 4 major clay mineral. Some like chemistry, illite chemistry.
Illite.
Crystallinity.
Crystallinity. Okay. Yeah. I know that crystallinity, but now we didn't check. Okay. You're right. We have to also that result I compare. We have to compare the in our data, but now we didn't. Or later I will have to check out that the crystallinity. Okay.
And whether the clay contents increased when you mentioned the monsoon is get stronger. With the clay content, why not show the green size result?
You mean that why illite increased during the monsoon strength? Right. Phillips era. Previous study. Phillips 2014. They report in the Irrawaddy River has many illite clay minerals. So during the stronger monsoon, maybe illite more physical weathering stronger in the Irrawaddy River. Okay. Yeah.
Thank you.
I'm going to present you my master result that I did between Bordeaux in France and Pondichéry in India. The results were published in Quaternary Science Review in 2015. So when I started this study, in contrast to the Asian and African monsoon, the Indian monsoon was poorly documented, especially considering its play and his impact on the Indian society. This natural process brings more than 80% of the annual rainfall in India. So understanding its natural variability, magnitude, and the physical process involved is a challenge for the present day and for the future policy predictions. And in the second time, some models suggest that the Indian monsoon variability could be impacted by regional processes. But few high temporal studies have been done to test this hypothesis. So it's why I choose to focus my study during 3 contrasting climate periods: the Holocene, so the actual interglacial, the enriched stadial 2, that correspond to strong iceberg discharge in the North Atlantic Ocean, and the last interglacial glacial transitions. And the aim of this study was to compare the paleodata climate with the model predictions, and to suggest some mechanisms to explain the Indian summer monsoon variations. So to come back at the beginning, yes, okay. During the summer months, so from June to September, the strong insolation induces an high atmospheric pressure gradient between the Indian Ocean, okay, and India that generates humid and warm wind that cross over India. It's the summer monsoon. In opposite, during the winter months, so from December to February, when the pressure gradients reverse due to low insolation, arid and cold wind cross over India from the East Asian continent to the Indian Ocean. So this study is based on two marine core located here at the outlet of two main Indian rivers, Mahanadi and Godavari rivers, which both cross over an area called the core monsoon zone. And the core monsoon zone is a key region to study a period of weak or intense monsoon, because in this area, the variation of rainfall during the months of August and July well represent the annual rainfall, the annual summer rainfall. So it's really region sensitive to the variation of the Indian summer monsoon. So the approach is palynology. So I use the pollen grains from these two marine core to reconstruct the past vegetation change in the core monsoon zone, so which is really sensitive to the Indian monsoon variations. Here, this map shows the repartitions of the vegetations in the Godavari and Mahanadi catchments. The core are located here. So each color represents an ecological formation which is sensitive to different environmental conditions. So on the land, the vegetation is composed by the open thorny vegetation, which grew up in relatively dry and arid conditions. Coming to the coast, this vegetation takes place to the tropical dry deciduous forest, mixing between herbs and trees, which extend in moister conditions. The green color represents the tropical moist deciduous forest, which is located more in the higher part of the Godavari and Mahanadi catchment, and which produce strong annual rainfall. Three communities share the coastal area: the mangrove, the marshland, and the coastal forest. The growth and the development of the mangrove is both impacted by the marine dynamic and fluvial inputs. The marshland is composed by herbs and halophytic species which occur in hypersaline area. And the coastal forest is composed by borasius and cocos trees, which need really strong annual rainfall to grow up. And the last point that I would like to underline is the Poaceae and Cyperaceae species that I plot together in the grassland community. These two cosmopolitan herbs present high percentage in my assemblages, and I choose to plot it together because it could mask some environmental variation. But because it's herb, we can assume that these species extend in open and dry environment. That means that their affinity close to the dry communities. The dry communities, sorry, I forgot to precise, the thorny vegetation, the tropical dry deciduous forest, the marshland, whereas the moist communities are the tropical moist deciduous forest, the coastal forest, and the mangrove. So here are the results for the Holocene between 11,000 years ago and the present day. I plot each ecological formations. So during the early Holocene, the vegetation is dominated by the moist community that produce really strong annual rainfall in India, so moist conditions. In opposite, during the late Holocene, the climate is become more arid, as recorded by the extent of the dry community as thorny vegetation and marshland. So to explain this long aridification trend, I choose to compare my data with the insolation, and I see that this long aridification trend vary in concert with the insolation variation. During the early Holocene, the insolation is high due to strong obliquity and low precision that increase the contrast between the land and the sea, and this process led to strong annual rainfall in India. In opposite, during the late Holocene, the insolation is low, so the insolation is a red curve. The insolation is low, that reduce the contrast between the land and the sea, and that explain drier condition in India. But my pollen assemblages show us another type of the variability. It's a rapid variability with the presence of most events in blue and drier events in red. And some of these events have counterpart in Europe. In Europe, in the European climate variability. It's the case, for example, for the first one, this one, well marked by the increase of the thorny vegetation, which could correspond to the Little Ice Age. The second one, in blue, is a Moster event, is well marked by the increase of the coastal forest, and it could correspond to the medieval climate anomaly. So how explain this rapid variability? Some models suggest the operation of feedback mechanism as, for example, the sea ice covers in the North Atlantic Ocean, the snow covers in the Himalayan area, or the variation of the temperature in the Pacific. And in fact, during the Little Ice Age, the strong expansion of the ice in the North Atlantic Ocean can explain global cooling in the northern hemisphere that shifts southwards both the polar front and the ITCZ. And this process could explain a reduction of the monsoon in India. In another time, in the Pacific Warp-Pool, a study recorded color assisted during the Little Ice Age. And this cold SST can explain a reduction of moisture in the summer wind in India. And opposite process could be at work during the medieval climate anomaly, so the moist period. So to summarize, during the Holocene, if the long-term trend seems to be impacted by the insolation, the rapid variability is forced by regional process feedback. Now I compare the most Holocene period marked by strong installation, the enriched stadial 2 that correspond to strong iceberg discharge in the North Atlantic Ocean, and the transition 5-4 that correspond to an interglacial transition. I plot the percentage of my ecological formation by patcher for a better comparison. So as I told you, during the moist Holocene, the vegetation is record relatively moist conditions, so a strong Indian monsoon. During the enriched stadial 2, the vegetation is mainly composed by the grassland and by the dry communities. That indicates that this time period corresponds to really arid period in India, so that traduce a weak Indian summer monsoon period. During the transition 5-4, the vegetation is composed first by the high percentage of dry community, so in orange, in yellow, sorry, in orange and in green. But by the emergence, by a change, an important change in the tropical dry deciduous forest, so in yellow. And this change is marked by the emergence of a genus, Artemisia. And this genus will expand during the dry condition, of course, but under a low seasonality, because it needs a constant annual rainfall to grow up. And that means that during this time period, yes, the Indian monsoon is weak, higher than during the interstadial 2, but weaker than during the Holocene. But we can record an intensification of the winter-summer monsoon by the emergence of this taxa. So now, if we take a look again to the insolation, indeed, the high insolation during the early Holocene can explain stronger monsoon period than during the enriched stadial 2 here and the transition 5-4 here. But if you look at the red curve, the insolation is quite similar during the enriched stadial 2 and during the transition 5-4. That means that the insolation can't explain drier condition recorded during the stadial 2, the enriched stadial 2. So to explain this drier condition, I suggest that the particularly arid climate during the enriched stadial 2 is forced both by low insolation and by a strong iceberg discharge in the North Atlantic Ocean that keep the high TCZ in the southward position in India. During the transition 5-4, the low insolation can explain the drier condition, and my pollen assemblages, by the presence of this new genus, record a low seasonality, so an increase of the winter monsoon, which can be induced by a high precipitation. It's a dashed line. And the main difference between the enriched stadial 2 and the transition 5-4 is the moderate discharge icebergs in the North Atlantic Ocean that keep in a northward position the high TCZ. In more northward position, the high TCZ than during the enriched stadial 2. So to summarize, the long-term change in the Indian monsoon intensity and seasonality will depend on the insolation. But the suborbital variability and the rapid variability is modulated by atmospheric teleconnection as iceberg discharge in the North Atlantic Ocean or sea surface temperature in the Pacific Ocean. So we record a stronger monsoon period during the early Holocene than during the late Holocene. The weakest Indian monsoon period is recorded during the enriched stadial 2 under low insolation context and strong iceberg discharge in the North Atlantic Ocean, whereas only a weak Indian monsoon intensity is recorded during the last interglacial glacial transition due to moderate iceberg discharge in the North Atlantic Ocean. Thank you for your attention.
The pollen records you showed for the Holocene, you showed at the beginning a map with two cores at the exit of two rivers. Yeah. Is it a combination of the two, or
no?
Maybe I missed it. You
no,
said
it's because I didn't I
Okay.
didn't tell. For the
Is it the southern one or the northern one?
For the Holocene, it was For the Holocene, it was the south one. It's this one in Godavari rivers.
Okay.
And the enriched saddle 2 and the last interglacial glacial transition, one in the north one.
Okay.
My name is Ji-Eun Kim, and I am a master's course student from Pusan National University. Today, I will give a presentation about the monsoon-induced denitrification change in the Eastern Arabian Sea during the last 1 million years. Within the marine nitrogen cycle, nitrate is important, playing as a key nutrient for primary production along with other nutrients like phosphate. Thus, we can call nitrate as a limiting factor for primary production, which is also significantly related to the marine carbon cycle. As you see in the presentation, there are several pathways in the nitrogen cycle, which include the nitrification at the oxic surface layer and denitrification at the suboxic subsurface layers. Now, during denitrification, instead of dissolved oxygen, nitrate is used as used to break down organic matter by bacteria under suboxic conditions. At this reaction, the lighter 14NO3 tends to be utilized easier by bacteria than the heavier 15NO3. Now, as a result, the nitrogen isotope ratio of nitrate in seawater can increase to 6 per mil or more. In addition, we know that during the nitrification process, nitrous oxide, which is a potential greenhouse gas for global warming, is produced and released. Now, explained just before, the dissolved oxygen in the seawater is removed by degradation of organic matter, and subsequently, nitrate can be used as an alternate electron acceptor for denitrification. Thus, denitrification takes place at places that are very low in DO concentration, and the Arabian Sea is known as one of the ideal hotspots for denitrification to take place. And in general, Arabian Sea takes up more than 30% of the whole global budget of denitrification. In the Arabian Sea, there are seasonal reversed wind patterns that are distinct due to different heat capacity of ocean and continent. Now, this is called the Arabian Sea monsoon as a continuation of the Indian monsoon. And by this way, denitrification in the Arabian Sea is intensified during strong southwest summer monsoons. When the upwelling at the western margin at Arabian Sea increases the productivity. Southwest monsoons tend to be intensified during interglacial periods when the increased heat capacity of continent tends to increase. So as a result, we can expect that the denitrification in the Arabian Sea enhances during interglacial periods. The oxygen minimum zone, or so-called the OMZ, is defined when dissolved oxygen falls lower than 0.2 milliliters per liter. And OMZ occurs between the depths of 200 and 1,000 meters, as you can see in the shaded part at the dissolved oxygen and nitrate profile. In particular, within this interval, nitrogen isotope ratios of nitrate in seawater are higher than 6 per mil because of the denitrification fractionation that I explained before. Thus, it can be easily seen why the Arabian Sea is famous for its perennial oxygen minimum zone. Now, in the early 2015, IODP Expedition 355 has sailed to the Arabian Sea, and this February, the results at Site 1456, which you see right here, has been published, as you see in the figure. Now, a couple of co-authors to this publication are also included in this presentation. Now, according to their results, denitrification occurred during the mid-Pliocene and Pleistocene periods. They judged the occurrence of denitrification by the del15N ratio, which you see here, reaching up to 6 per mil and more. In addition, such denitrification has been maintained during the last 1 billion years with the increase of TOC and TN, which are an indicator of productivity increase. So the objective of this research I am presenting is to reveal the denitrification history during the last 1 million years at the same site, 1456, in the Eastern Arabian Sea. Now, particularly, we focused on the degree of denitrification using del15N values from bulk sediments that is in response to glacial and interglacial periods. We worked on Unit 1, which occupies the uppermost part of Site 1456, which is about 146 CCSF meters. As you see, the lithology of this unit is very diverse, consisting mainly of pelagic carbonate woos and hemipelagic sand, silt, and clay, which are derived from the Indus River. Now, frequent occurrences of turbidites are characterized by the erosional contacts you see. Frankly speaking, such lithology is not most favorable for paleoceanographic study, for such features are regarded to be one of the primary difficulties on constructing a chronological correlation for precise age model of sediments deposited. However, despite of these difficulties that I mentioned, we tried to construct an age model of oxygen using oxygen isotope ratios. A total of 268 samples were obtained from a composite section of Unit 1 consisting of holes 1456A and 1456C. Then we measured the oxygen isotope values from a planktonic foraminifera, the Globigerinoids ruber. The results are shown on the left, with the red and blue lines dotted curve indicating the oxygen isotope profile in depth scales. These numbers on the right, on the left, are the numbers that are obtained from the shipboard biostratigraphy data. This horizon marks the Bruns Matsuyama boundary, also identified by the shipboard scientists. Now, in our lab, we also found the disappearance of pink G-ruber, which indicates about 120,000 years ago. Under such circumstances, we try to correlate our oxygen isotope stratigraphy profile to the LR04 stack in the middle of the plot as a global chronologic reference. Finally, we obtained the age chronology of oxygen isotope stratigraphy that takes us back to as far as 1.2 million years, covering up to marine isotope stage 35 and 36. The shading represents the glacial periods and the white represents the interglacial periods. Now I will present the denitrification history at site 1456 in the Eastern Arabian Sea. The left profile is the oxygen isotope stratigraphy that we have just seen, and the right profile is the corresponding del15N variations. It can be clearly seen, actually, that the del15N values tend to be higher at the white interglacial periods and lower during the shaded glacial periods. The interglacial values are much higher than the global deep water average of del15N, which is about 5 per mil. And the denitrification criteria is the same 6 per mil as the previous research I have shown you. Now, by this result, we can interpret that the denitrification has consistently been persistently happened during the last 1.2 million years, and their fluctuations have been coinciding with the monsoon strength variation, which is also related to the glacial interglacial cycles. Now, I would like to compare our results to the Western counterpart. Site ODP 722b has been is located near the Oman margin at the Western Arabian Sea, and the del15N values have been reported by Altabet et al. 1999. And this figure is the comparison between the del 15N values of variations between site 1456 and 722b, with the black line indicating 1456 and the red line indicating 722b. Two sites tend to look similar in the variation, but there are several comparisons that we can acknowledge. The first one is the minimum value of nitrogen isotope ratio. For site 1456, the black line tends to have a higher minimum value of del 15N. Such difference can be explained by either perennial OMZ effect or early diagenesis, or maybe both. Site 1456, as I've shown you in the beginning, is located closer to the perennial OMZ that avoids a total collapse of denitrification during glacial periods. Thus, perennial OMZ effect is efficient even when the denitrification is expired in the western side. Now, the latter possibility of early diagenesis can actually be evaluated because the relationship between del 15N and Tn, which is an early diagenesis, is used to know the effect of early diagenesis, is not significant with an R squared that equals 0.12. So early diagenesis in this area seems not potential. Second, the correlation of del 15N variations between two sites look positive, like I said, and thus we can conclude that the Arabian Sea has experienced consistent denitrification as whole despite the regional degree difference. Now, to summarize my talk, Unit 1 at site 1456 in the eastern Arabian Sea holds record of the past 1 million years of denitrification by showing higher del 15N values during interglacial periods and lower del 15N values during the glacial periods. Further studies will probably focus on the glacial interglacial productivity change that affects the degree of denitrification, and I will try to show insight to the mechanism that strengthens the OMZ in the eastern Arabian Sea. Thank you.
So yeah, this talk is about the African atmospheric dynamics and the marine productivity of the Congo River mouth. So it was motivated by a collaboration with the authors of Hardy et al. 2016. In the paper, they analyzed the sediment core Kasai-01 here of the Congo River mouth, for which you have the Congo Basin represented here. And by using dinoflagellate assemblages, they could reconstruct several variables such as productivity or river runoff. So this is a figure from the paper, where you have here as a function of time in brown the productivity index, where they show that productivity was higher during the Holocene period than during the isotopic stage 3, and productivity during the isotopic stage 3 was also slightly higher than during the last glacial maximum. Thanks to different kind of dinoflagellate species sensitive to salinity, for instance, and the reconstruction of the amount of heterogeneous input, they could see that the river runoff was strongly higher during the Holocene period, and so they hypothesized that the strong increase in productivity in the Holocene was due to a strong increase in the river runoff, which brought more river nutrients to the region. Similarly, a slight increase in the runoff in the isotopic stage 3 is responsible for higher productivity than during the LGM, for which the changes in productivity were mainly linked to changes in the upwelling activity. So the aim of this collaboration was to get more insights on the link between the observed local variations in the core, in the region, and the large-scale dynamics over Africa by using a climate model. So we use the IPL cell coupled model, which simulates the interactions between the atmosphere, the continental surfaces, and the ocean, and simulates the marine biogeochemistry as well. We did 5 climate simulations by changing the climate forcing, such as the astronomical parameters, the ice sheet cover, and the greenhouse gas concentration. So we have 3 interglacial simulation, a pre-industrial one named Control, 2 Holocene simulation here, 1 less glacial simulation, and an isotopic stage 3 simulation. So the 2 last one are glacial states. So in our simulation, productivity is a function of light, nutrients, and temperature, and the sources of nutrients in the model are the ocean itself, the atmospheric dust deposition, and the river inputs. However, in our simulation, the river nutrient inputs were constant in time, which means that they did not vary with the amount of runoff, and they were also constant between the different climate states. So with this simulation, we could not test directly the effect of the river nutrient inputs on productivity. However, what we could do was to look at the simulated changes in river runoff and how they were linked to the atmospheric changes. And we could also look at the modeled productivity to see what we could learn from such a model. So these plots represent the Congo runoff as a function of precipitation over the Congo basin for each month of the year, so the different colors for the 100 years of each simulation, the early Holocene, the last glacial maximum, and the isotopic stage 3. What we can see as expected is that as the precipitation increases, the river runoff also increases. We also clearly see a strong reduction in precipitation and runoff in the LGM simulation compared to the early Holocene, and as well a reduction in precipitation and runoff in isotopic stage 3 that is slightly less intense than in the LGM compared to the early Holocene. So these changes in runoff and precipitation are coherent with the reconstruction of the sediment core of Hardy et al. So now what we wanted to do is to link these precipitation changes to the large-scale dynamics, and we're going to focus on 2 seasons. So the first one being the austral summer, the reddish point, in which we can see that the largest changes in precipitation occurred between the different climate states, and on the boreal summer here, the bluish point. So this is the precipitation mean state in our pre-industrial simulation here in the over the African region. What we can see is that it's the humid period for the southern Africa with the tropical rain belt situated here. And these are the plots of the difference between the precipitation in early Holocene and LGM compared to the pre-industrial. What we can see is that over the Congo Basin area, the changes in precipitation in early Holocene simulation are quite small. Quite small. However, if we look at the LGM simulation, we see this strong reduction in precipitation, which can be explained by a strong reduction here in the specific humidity compared to the pre-industrial, because we are the LGM. So this is due to a strong thermal effect, the LGM being a colder climate with less greenhouse gas. And so it reduces the evaporation and recycling over the continent, and there's the precipitation. So the same pattern as is found for the isotopic stage 3, so comparable to the LGM, but with less intense changes. If we look now at the boreal summer, so the tropical rain belt now is situated around 10 degrees north, and it's the humid period for northern Africa. Over the Congo Basin, we see that changes in precipitation are quite small compared to what we've seen in austral summer, with a slight intensification over in the early Holocene as well as in the LGM compared to the pre-industrial. However, what we also see that's interesting, it's what's happening in the northern Africa, where you have a strong increase in precipitation in the early Holocene, as well as isotopic stage 3, due to northward shift of the tropical rain belt. These changes in precipitation can be explained by the dynamics, by changes in the wind patterns. So this is the mean surface winds in the pre-industrial, where you have strong southeasterly trades and northeasterly trade winds that converges around 10 degrees north, bringing all the moisture over the ocean there. And you have these winds that enters the continent here, the monsoon winds, which bring moisture to the northern Africa. In the early Holocene simulation, we see, so the insolation is stronger in northern hemisphere, which acts as reducing what we see is that we have a slight increase in the trades in the southern hemisphere and a reduction in the trades in the northern hemisphere. And so this led to a shift in the wind patterns and allows for the operation of this westerly flow here, which brings the humidity from the ocean to the continent into northern Africa, and is responsible for higher precipitation in this region. In the last glacial simulation, we have this strong increase in the trade winds characteristic of the glacial simulation, which does not allow for this strong apparition of a stronger monsoon flow in these glacial climates. However, what's interesting to note is what's happening in the isotopic stage 3 simulation, where you have both the contribution of the glacial states with stronger trade winds, and also the contribution of a higher insolation climate with the apparition of this enhanced westerly flow, which bring the moisture over northern Africa and can explain the higher precipitation in this region. So we've looked at productivity over a small area of the Congo River mouth here. And so we represent here the seasonal cycle of marine productivity integrated in the first 300 meters in this area. And what you can see is that the Holocene productivity in red and orange curves is always higher than the LGM and isotopic stage 3 productivity in green and purple. So that's surprising because we have the same results as in the sediment core, even though we do not have the nutrient variation in the river. So either this hypothesis is not, the hypothesis that the river nutrients drive productivity is not, I would say that the river nutrients is not a strong driver of productivity, or either the mechanisms behind the productivity change in our model are maybe not realistic. So this is just preliminary work, so we have to do more analysis on the mechanisms behind productivity changes in our model to understand more so these mechanisms and to see what we can learn from the different climate states. So however, we did a sensitivity test of the marine productivity response to the river nutrient concentration. So just look at the simple lines here. So you have, this is a profile of productivity as a function of depth. The black line is the productivity in the LGM simulation, and the blue line is the productivity in a simulation that is in every point similar to this LGM simulation, except that we reduced the nutrient river input by 20%. What we see is that if we reduce this input of nutrients from the river, productivity is reduced as well of the Congo River mass. So that supports the hypothesis of the influence of the river nutrients on the productivity in this area. However, what we can see is that in the region, at least in our simulation, productivity is as a strong maximum subsurface peak that, which explains most of the productivity in the region, and that when we reduce the nutrients, the effect is mainly limited above this large productivity peak. So we can still wonder if the changes in the river nutrient supply will have a significant effect on the overall productivity signal that will be recorded in the sediment. So as a conclusion, we've seen interesting changes in the surface wind and precipitation over Africa, especially in the boreal summer. However, we've seen that the Congo River runoff is mainly affected during the austral summer when we have a strong thermal effect of the in the LGM and isotopic stage 3, which reduces the precipitation over the basin. For productivity, we've seen that our model shows variations in agreement with the reconstruction, whereas we do not have the river nutrient inputs changing through time. And the sensitivity tests show that lower river nutrient inputs indeed induces lower surface productivity. So we need to do a little bit more work on the mechanisms behind productivity change, especially in our model. So the limitations of this work are obviously the constant river nutrient supply. So we could test, for instance, different nutrient values depending on the amount of runoff between the different climate states. This was also a coarse resolution model, and so it cannot represent very well the small-scale dynamics as the upwelling near the coast, and so that can explain why we have this signal in productivity. In the model, however, we expect the model to simulate a correct sign of changes between the different simulations. So to counteract this kind of problem, we could use a regional high-resolution model to study more precisely the mechanisms behind productivity changes and to disentangle the effect of the river and of the ocean circulation, the wind stress, and so on. And finally, so we've seen interesting patterns of precipitation and winds, and we could use precipitation and wind proxies to see if they can corroborate what we see in the simulation. So thank you for your attention, and if you want more details, I have a poster on the Indian summer monsoon this afternoon, so you can come to see me. Right, thank you.